right. Hello, everyone. Thanks for coming to this session. Today, I'm showing you around a favorite project of mine called Crow. Some of you may have heard of it, some of you may not. I want to show you how to build composable Kubernetes APIs, maybe in a different way that you're used to. Some of you may have already worked with other tools that try to do similar things, such as Crossplane, so you may see some similarities. But this talk is really focused around trying to define why Crow was built, why we are working on Crow right now, what Crow is even supposed to bring to you, and what you can take away from this session probably will also influence how you look at Kubernetes APIs in the future. In general, who am I? Hello, I'm Jakob. I'm basically involved in open source since the beginning of my career. I've been at Red Hat, mostly at SAP, and I've worked as the Crow main maintainer alongside Amin, who is from AWS, since Crow 0.3 roundabout, so roughly 1.5 years ago now. And what we have been doing is we've been building Crow as an independent, I would say platform engineering tool. So if you come from platform engineering, you will probably find some of these concepts familiar, but I will still go ahead and try to explain some of them along the way. In general, I'm also involved in some other things, for example, the Neonifos Foundation, so you may see me involved in some other projects as well. Right, now to the fun stuff, to the project. What is Crow? Crow stands for Kube, or Kubernetes Resource Orchestrator, and is a Kubernetes SIG cloud provider project. And it lets you turn any set of Kubernetes resources into a reusable API. What does this mean? This means you define one schema and you describe the many resources that you want to orchestrate together in that one schema. And then you can basically connect them with CEL expressions. We will get to that. So we have inbuilt expression languages as constructs, and that makes it so that you can connect arbitrary resources together. And these resources then become one single unit of work that you can orchestrate and work with in your cluster. So it's a way of providing abstractions, and it's a way to manage API sprawl. Those of you who know Kubernetes since the early days may still remember a time when deployment was the magic thing and it just became GA. These times are long gone, and no one really works with deployments as a native API anymore. Instead, we have tons and tons of extensions, custom resource definitions, and APIs that make the platform truly yours. But if you have hundreds of these, things become very, very hard very quickly, especially if you try to bring adoption into your platform, into your cluster. And at that point, you need to build some sort of abstraction layer, and this is where Crow comes in. Crow is basically a glue code layer that allows you to compose arbitrary APIs into one single unified API so that it is manageable again from a platform perspective. How do we do this? We have this concept of a resource graph definition. It's very self-explanatory in my opinion. So it basically defines a resource graph that combines these resources together. And it's a sort of blueprint. It's an interface that you define, and this interface can then be reused, and it will be translated into a CRD that can be then used as an abstraction over other APIs. How is that nice? That is nice because once you create this RGD, we are able to infer from the schemas of the underlying resources if there are any issues that you have. For example, if you have a replica count or something, you know it's an integer from the schema, right? And we know that it's an integer, and we make sure that you can only pass it to functions or other fields that are compatible with such, right? So it's very nice because it's not this typical, I just have a script running and the script breaks when it runs kind of moment, but you really have a definition that you can apply to the cluster in advance. Then it checks for the schema guarantees, and then you run with the instances where you already know the schema has been validated up front. So you basically have a static type checking ability up front, which you usually don't get when working with expression languages. Now, also, I want to say a few words around how it actually works. Basically, we have a dynamic controller that runs behind the scenes and does all of the heavy lifting for you. It's one single controller. It's very lightweight. So you apply one controller. You can do it via Helm chart or the normal shenanigans. It does not really matter for us. And this one controller then brings with it the entire orchestration capability. Everything else is basically up to you. How does it work? We have this resource graph definition that I already talked about, and then inside this resource graph definition, you define a schema. This schema gets translated into a custom resource definition that you can then reuse, and you have resource templates. These resource templates are very special because these resource templates allow you to reference fields from the schema or from other resources. That allows us to use this expression language as a kind of implicit builder structure for a graph that we build behind the scenes. So what we can do is we can connect and map objects such as deployment to other objects such as a config map or a bucket from S3 or any other API. And the nice part about this is because Crow knows about these expressions and has this static type checking capability, it can infer the order of application and updating automatically. So unlike maybe traditional engines that you're used to that have this pipeline ability in them, right, where you go one step to the next and you explicitly define what you want to do after what, you now have an implicit dependency declaration ability. This is very powerful because it allows you to derive very, very complex definitions and very complex dependency chains without ever having to code them manually. You basically already have them implicitly by just referencing fields from each other. How does it look in practice? The way that it works is you start with an RGD, with a resource graph definition that defines some fields inside of them. These get translated to a CRD through which you can create instances. This is just like any other CRD. You are used to this. This is nothing special for anyone that has worked with Kubernetes. Now the magic happens. Crow detects that this instance was generated and dynamically watches instances of this CRD and then translates them to a resource graph behind the scenes that has all this knowledge of all the expressions behind the scenes already stored in a cache. Then it can go and dynamically apply and update these objects in the correct order and can then also update them in the correct order continuously without ever failing out. So it's a way of continuously reconciling just like any other controller, but it works with any resource that you have defined. Now, how is Crow special? There are a few caveats to it. There's a few caveats to Crow in general that you maybe are not used to. The first one is simple schema. What is simple schema? Simple schema is basically an easier version of OpenAPI schemas that we have written specifically so that it's much easier to define your schemas in an RGD. Simple schemas are a very simple syntax that translates directly to OpenAPI schemas, but that is much, much nicer to read as a human. So it's much nicer to maintain and to operate with. You can see that there are many equivalents, and it's really nothing special to anyone who has ever worked with it. It's just a much smaller syntax set so that it's more condensed. And then there's another thing that I want to point out. Many engines that do orchestration in Kubernetes struggle with operating on existing data, and Crow has the ability to not only impose new resources that it creates on their own, but you can also reference already existing material in the cluster and make it part of your graph. That is very powerful. For example, if you have dev, stage, and prod clusters, and you have already running configurations that you run all the time, then you don't need to define these explicitly by creating them in every object that you have defined in the graph, but you can just reference this as an existing object, make it part of your API, and then just use the data out of the config maps, for example. Now, how do we use CEL? CEL is very special. CEL stands for Common Expression Language. It's a language that is basically written by Google to be very, very fast at evaluating once you have an expression evaluated. This is very powerful for us because we can use this expression engine as a baseline for all of our graph work. What we do is we just basically take apart the expression, check I would call it the expression path, for example, schema.field, and we translate it into a node in the graph. And the way that we do this is very nice because we have the ability to just take the expression once from this resource graph definition, cache it for all of the instances, and then just evaluate this expression all over again. This allows us to go hyperscale, and we have tested Crow with up to 2,000 instances on a single RGD without having more than 10 milliseconds latency on the controller. And we have had clusters that run with hundreds of thousands of instances actually already running in prod. So this should show you how scalable Crow as a system can be when you really drive it to the extremes. You also have the ability to do conditionals, and that is very nice as well, because we can use the expression language to define something like an if structure. So you can do something like enable monitoring, and if enable monitoring is set to true, you can encode a service monitor, for example, in your Prometheus stack. So you can also reuse these in a dev landscape or in another setup. You can also do much crazier things. For example, you can do vendor freeing by, for example, encoding different enums for AWS or GCP or whatever, and you have different configs that get pulled in on demand. So stuff that you would typically not get out of a pure expression language, but that you can get dynamically when evaluating against these instances. So for example, for cluster 1, you can have an instance that is returning on true and another one with false. Now, overall, why should we use CEL? Basically, what I already said, you have the ability to have very nice functions that you can define at runtime. So we can do things such as ranges that allow you to create thousands of resources at once just from a simple loop. And you also get these nice runtime properties of CEL as an expression language. That means it always terminates, you have no side effects that can occur, and you have type checking at apply time that I already mentioned, right? Because we can encode the CEL expression to the schema that is behind the CRD or the API that you're using. And also you have an audit capability because you know exactly which expression led to which result. This is very nice if you run at scale, and it's also the reason why, for example, policies in upstream Kubernetes also use CEL. So this capability of having this nice bounded language as a construct works very well in these situations. Now, I want to show you this because it's super simple. I want to basically go ahead and define my own RGD, and I'm just going to show you this now. The way that this works is you define this RGD, right? I already talked about this. I hope you can see it. I maybe make it a bit larger. And this RGD has then a set of resources inside of it. I just use a deployment service in Ingress. Forgive me, I'm not using Gateway API, but it's much simpler. So now I have this setup here. And what this does is it gives me this set of resources that I define. And you can see these weird syntax expressions here. And this is the CEL expression that I use inside of the RGD. You can see here that it defines a node called schema. This is a node that is inserted by Crow. Every time that you define an instance, you can then reference the field from the value from that instance. So in this case, schema spec name gives me the value of the name field in the spec. And also what I can do is I can connect different objects together. So for example, I have a service here, and now I can use a defined field such as the label selector from the deployment, and I can inject it into my service. So you no longer have this typical problem like you have in Helm charts where you have to constantly make sure that everything is aligned with one template expression, and you go nuts trying to maintain it all. And then also you can connect any other API, and you can do crazy syntax schemes, but I'm not going to go into this. I think the most important part is this here now, the schema. I just defined a schema that I call application. You can call this anything that you want, really. This is what's going to be exposed to your users or to your cluster. This means that now whenever I create an instance of the type kind application, behind the scenes, this graph will get used, and it will start to create in the topological order, we will get to that, all of the resources that I defined. So in this case, I have a topological order here of the deployment, the service, and the ingress very easily, right? So that means I create first the deployment, update the deployment, then there comes the service, and then there comes the ingress. There are many more crazy things that you can do here. This is really just to showcase the point of how this system works. You can do many dependencies. You can do thousands of nodes in a graph. We have had cases where we observed basically setups where even entire clusters got cross-managed with, I would say, I think the most we tested was like 3,000 nodes. So you can really go crazy with it, right? And Crow doesn't really have an issue with it. I think the interesting part is that it's super low overhead, right? So the only thing that gets created behind the scenes here is really the CRD for the RGD that we already have from the shipment of Crow itself. And then we have the application here. And the application is basically the result of the schema, and that's nothing special as well. This is basically just the API that Crow watches. And now when I have such an application, I can basically use a very simple API. So in this case, I can just call an image or an ingress, and these are my spec fields that I reference. And this will automatically lead to objects that are being created on the cluster that have integrated all of the management capabilities of Crow. So you can see here that the service was created that was managed by Crow and has the injected fields. You can also see the app selector that got injected from the deployment, right? And there you can really see how this works. Obviously, very simple stuff, again, just for conceptualization. You all know when you run things in prod, the real important part is when you update, and this is when the graph comes in, basically. So when we update the instance, it will go in this topological order, it will do the updating. You can do even crazier things like blue-green deployments with this, but I'm going to refer to the Crow website here because this is going to explode it otherwise. Now, what does this mean for you? This is one of the first times, in my opinion, where you are truly free from any ecosystem whatsoever, and you can compose any API whatsoever at runtime. No longer at deploy time, meaning you don't have to use a Helm chart or a customization anymore to orchestrate your stuff, but instead you can offer an API at runtime for your platform that already provides an abstraction out of the box. It also means that you basically have an inbuilt awareness of the ordering and the dependencies between objects, so you no longer need to explicitly encode this. This means you no longer have to worry about a pipeline structure or an explicit dependency declaration because this is inbuilt. Also, you can use it to build higher level abstractions because it allows you to coordinate and manage already existing operators in a way that fits for you. Every cluster can look different. The way that you use Crow can be completely different from the way that I use Crow. And the beautiful thing about it is we don't mind it. We are very unopinionated. And because it's part of the cloud provider, there's a huge interest in keeping it vendor neutral at all times, right? So we have interest and involvement from all the major cloud players. We have AWS involved, we have Google involved, Microsoft involved, I'm involved with SAP. So it's like everyone can join on this. And this is really, for me, a very beautiful thing. And also, it allows you to be scale-ready glue code. I really like this because it's the first time for me that I really felt that it clicked for me and I didn't have to do crazy custom scripting to aggregate stuff or build my own operator to build custom logic to operate within hundreds of resources, right? How else do you manage it? You usually build a cube builder operator or you use any of the other frameworks that are out there. You no longer have to do this for the most basic of scenarios, really. And it's just something that you can put into your platform and you can even make it part of the platform itself. You can make this abstraction ability part of your user API. You can make users define their own APIs. There are very powerful use cases that get enabled because its syntax is so simple. There's also some crazy things that you can do because you can nest RGDs in other RGDs. So what you can do is you can basically build very, very custom nested composed graphs that all come back together to one big graph. You can define an RGD that creates a CRD that is then defining another RGD as part of its resources, right? So it's very cool because you can define basically entire product definitions and entire product architectures just within CRDs in these graphs. And you can also do very cool things such as abstracting away opinion. For example, all of your deployments always must have that one annotation. What do you create? You create your own my company deployment, and it will always have that one annotation inside. And because it's so low overhead, no one will ever notice, and it will always have the entire deployment status inside its status as well, right? You can do things like multi-resource RGDs, what I just showed you, connecting any arbitrary resources together and having them in one API. And then you can combine all of this, and you can have a database RGD, an application RGD, a monitoring RGD, right? Whatever you want, and you can map them all together in one product RGD. This is very cool because it allows you to abstract usual platform capabilities like blue-green deployments or whatnot. You can think of whichever feature insert here, and you can just abstract things away. At the same time, the features behind it stay simple. It's always this topological ordering, you have a dependency expression, you have a status exposure, and it never changes, right? So there's never the question of how does it work or why does it behave like that? Why is it magic? Because you will always have this expressed graph with a topology inside it, and you can always see, this is where, for example, my node failed. You can see when the syntax failed. You can see when the expression failed, when the schema doesn't match. All of this is very visible to you, and it's unlike any traditional schema solution that we had before. Now, best practices, obviously, same thing as with any other coding. You need to keep these RGDs small and focused. That means make the compartmentalization of these abstractions very small. You can expose status elements in the instances. So for example, if you have a deployment and an ingress, you could expose the status of the ingress together with the deployment replica count in one status element, and it would be part of your product API. You can then encode this again in other solutions, for example, Backstage, and then you suddenly have a total UI on top of it. So there are many crazy things that you can do without a lot of effort. You can, and obviously should, use naming to your advantage. So it's basically programming 101. And the nice part is, because the syntax is so simple, you can just plop an AI agent of your choice as well, and it will just build the abstraction for you. Just as an experiment, install Crow on a canary cluster of yours and just tell it to derive an API abstraction for your own deployment of your product, and you will be amazed at how fast it actually gives you an abstraction that is nice. And obviously consider the chaining depth. Like with any abstraction, don't overdo it. I think the most important part with any tool is that it has its purpose, but you shouldn't overuse it. I don't want to say that it's the magic solution for everything, but I truly believe that it is like a missing piece right now that you can just plug in and plug out as you need it or want it. If you're interested, I recommend that you check out crow.run, because I took a lot of the examples and use cases from there. It has also a lot of nice other examples that you can use to explore some of the advanced use cases that I just outlined. And obviously, I would be super happy to see you in the community. Thanks a lot. Are there any questions? Yes.
Thank you. I have a question about the runtime APIs. How does this, or how do you see this working together with GitOps? Because if you pull the whole API definitions into runtime, then suddenly the maintenance of which APIs are now existing, where you can access them, what versions they are, and so on and so forth, gets really messy, which the classic GitOps would pull into like, hey, we have this in Git, don't look at the cluster, just like do what we have in Git. How do you look at that? Do you think it needs to work together, or how do you use that yourself?
So I think GitOps is great. I think you should use GitOps to manage your clusters. I personally think that if you use, for example, the RGDs, then you can just maintain them in GitOps as well. I think it's part of a platform experience like any other. So usually what you would do is you would roll out the RGDs as part of your cluster setup. And then when you have platform teams, they will basically maintain these for you. And then when you have an application team that actually operates on that cluster, they would just use these APIs. And because they're documented in Kubernetes, you can use them in a Helm chart too, right? That's not really an issue. You can also use RGDs as like a CRD equivalent, right? So you can set them up as prerequisites, and then you can just build instances of these RGDs into your Helm chart. It's not a problem at all. I don't think that it's really contradictory. Obviously, there's the question of the chicken egg problem, right? Like what comes first? And there the answer is you can simply use your favorite GitOps tooling of choice, and it will just be eventually consistent, right? So you can just roll out the RGD alongside the instance, and the instance will wait until the CRD is there and then be applied normally. So many questions. Yes?
Thanks. Can you maybe say what differentiates Crow from Crossplane, or when you would still build your own operator?
So I think Crossplane and Crow have a lot of similarities in many regards. There's even a joint project, it's called Crossplane Function Crow, that has basically the ability to embed the Crow graph ability into a Crossplane composition if you want that. But Crossplane compositions by nature are explicit. So a lot of the composition definition itself is very, I would say, more verbose, because there's not this implicit ability to define an ordering, right? That said, you can do a lot of things in compositions as well. Where you find trouble is when you do upgrading and when you do schema management. Then I would argue that runtime support for the ordering itself is probably beneficial. This is the main difference number one, and the main difference number two is it's vendor free. So it's part of Kubernetes upstream, right, through the cloud provider. So by definition, it's not backed by one single company, and I personally find this beneficial as well. There were 2 more questions, I think. Yeah, feel free. Whoever.
You mentioned upgrading the instances, but what if I want to roll out a new version of my resource graph?
So in this case, we have a concept, you maybe have seen it in the demo already. It's called resource graph revision. So basically we have revisions just like in a deployment with a replica set, right, where we basically roll out changes of the resource graph over time, and we then basically transition from one revision to the next slowly and steadily, right? So this is basically how we solve that. There's also more work upcoming. So if you're interested in this, we have a huge PR coming in for the concept of a graph that defines Crow itself. So this will be very fun. It's an 80,000 liner if you're really interested, but we will see about that.
You mentioned about the interface to the end user, exposing something simple and let them play around. And combined together, you mentioned also the ability to, like, the suggestion to compartmentalize or creating a scope for each specific proposition. How that can be aligned? For example, I play around with Crow and also with the Crossplane. And the first problem that I face is exactly this fragmentation. Then you end up with, I don't know, web application 1, web application 2, web application 3, versus maybe creating a simple Helm chart can solve and template for you.
I think
you lose all of the benefits, fair enough.
100%. I think in truth, this for me is a sign of abstracting a bit too much maybe. So if you have like 3 CRDs for 3 different fields, maybe it's time to step a little back, right? And say, okay, maybe you don't need this. I think the ability to abstract does not mean you have to abstract, right? So just because you can define a lot of things in Crow does not mean you should or have to, right? I think Crow should just be used when you want to hide certain complexities on purpose, also for the sake of maintainability or support, right, or ease of use. But it does not mean that you have to now suddenly hide every API behind another API. That's not its purpose, right? I think in general, it's very easy to misuse a powerful construct, and it is also very easy to misuse Crow, right? If you don't define a schema that is generic enough or that is not scalable enough, then you very easily end up with the same issues as with every other API. So API design still is important, right? It just allows you to define an API over other APIs very simply. That does not mean the API is hard or easy to write.
Yeah, thanks.
Hi, is there a multi-cluster support for Crow?
I love that you asked this. In progress. Not yet. All right. Then, thanks everyone.